I said on there, I believe it is Tuesday the 4th, okay, of May. That's when your write-ups will be due. If you want to turn them in earlier, that would be helpful to me, but I know that may not be helpful to you. So you can see how that works, okay. And then there'll be the final will be as scheduled a little later on. Any questions about logistics or technical matters? Okay. If not, I'd like to talk about, again, this is now, I think, lecture 23 of the discrete math class. I'd like to start talking about the problem of coloring graphs, okay, which is, again, we've been marching through different sort of invariants or structures or properties of graphs. Graph coloring is an interesting problem that comes up in a lot of different applications. And it's one of these things that you know, you need to know a little bit of graph theory to recognize where it comes up, okay? But it comes up in a lot of different applications. So let's look at an example. Suppose, let's say, that we had a school that wanted to try to minimize the number of final exam periods it offered. You know, you guys are going to have your final exams scattered over a week or so, okay, where there's like 3 periods a day for a week. Okay, that's like 15 different exam periods the university is offering. Suppose we had a university that wanted to, instead of pre-assigning all the exam periods based on the calendar, wanted to minimize the number of exams periods it actually used, okay, over the entire school. Now, what do you want to do to schedule exams? Well, the school has a certain number of courses that it offers, okay? And there's no problems teaching having 2 courses scheduled at the same time, okay? Provided there is no student in both of those classes, correct? There's no problem with scheduling CSE 547 and English 309, okay, at the same time, unless somebody in the class happens to be in both English 309 and CSE 547. So one way that we could model the problem, if we wanted to minimize how many exam periods we needed, okay, is we could build a course where, a graph, where we have a vertex for every single course, okay, that's being offered, okay, and an edge between any 2 courses which have a student in common, okay. So that's what we're going to be modeling this graph. So if we look at this here, Gopal on this chart here is taking both 502 and 532. KK is an industrious student, okay. He was taking 3 different classes, okay, and that explains why there are 3. Well, that explains why there's 3 different edges here. Every pair, the 3 courses he's taking is this, this, and this. Every pair of courses in the set that he's taking, we add an edge between, okay. So, because you can't schedule any of these classes at the same time. That said, now let's figure out what is the minimum number of class. First, any questions about what the graph is? Okay. The question now is, how do we figure out what's the minimum number of time periods you need in order to schedule this thing? We could schedule any 2 classes at the same time, all classes at different times, but that would be a lot of different exam periods. What I claim we want to do is to find a way to color the vertices of this graph, namely to color the courses, okay, in such a way that no 2 vertices connected by an edge get the same color. Okay, and further, we want to minimize so that we minimize the total number of colors used. That, I claim, is the most efficient schedule that you can have, okay, in terms of minimizing the number of periods. Why do we want the constraint to be that no 2 courses connected by an edge can be colored at the same color? Well, the colors are going to represent exam periods. Later on, we'll say, exam period, purple. The purple courses will be scheduled for 8 in the morning. Okay, the green classes will be scheduled for 11 in the morning. Okay, but the important constraint here is that since we have whenever we have an edge between two vertices, that means that they cannot be scheduled at the same time. And so by enforcing our coloring scheme such that any two vertices connected by an edge have different colors, we guarantee that we get no conflicts in our schedule. Okay? So I claim that graph coloring is the right way to model this problem. How many people sort of see what I'm saying so far? Are there any questions about what this actually means? Okay? So again, in this particular graph, okay, if we take a look at it, the only pair of courses that are not actually connected by an edge turn out to be 502 and 533. So we could color both of those green, okay, and then we're forced to color this thing something purple, pink, and maroon, okay, because they're all connected. You know, otherwise there's an edge between this and this, so this can't be the same. This and this, so that can't be the same, and this, so that can't be the same. Okay? Any questions? Okay? So the interesting thing about graph coloring, the reason why it becomes an important problem, a lot of different scheduling problems can be reduced to graph coloring. Okay? Because basically what we're trying to do, whenever you're trying to schedule things so that certain things are not allowed to happen at the same time, that is usually reduced to being a graph coloring problem. One place where you always hear of graph coloring problems coming up is in compiler optimization. Okay? When, let's say, you want to write a compiler, okay, what's a compiler? A compiler is a program that translates programs written in a level programming language to a lower level thing. One thing that comes up a lot is how do you use registers? Okay, if you think about, if those of you know about how computers are organized, internally you've got a small number of registers in a computer, okay, you know, that are sort of the high-speed, fast things, okay? And so long as you stick the data in these registers, you can compute on them much more quickly than if it sits in memory. Okay? Now the problem is you've got a small number of registers, okay? And the goal in trying to do a computation, okay, is to figure out one of the critical things in optimizing it turns out to be how do you schedule the registers, okay, so that you have to change, okay, things as infrequently as possible, move things to memory as infrequently as possible. And the classic way to model something like that is with graph coloring, okay? I didn't actually give you the graph that does that, and that takes a certain amount of modeling to see that, okay? But graph coloring comes up whenever you have a scheduling problem, it seems, okay? And it's important to know about that. Any questions about what graph coloring is? Okay, so it's a useful thing to know about. And it's one of these things that if you don't know some graph theory, you usually cannot see how to model these things. Okay? So now let's talk about, instead of the application of graph coloring, let's now talk about it from a more theoretical perspective, okay, or what we talk about when we talk about in the sense of graph theory. We say that the chromatic number of a graph, okay, is the minimum number of colors with which it is possible to color it. Okay? Now, if I give you an n-vertex graph, can somebody tell me how to color it using n colors? Okay? How would you, if I give you any n-vertex graph, is it possible to always color it using n distinct colors? And the answer is sure. If you color every single vertex a different color, then any edge connects pairs of vertices of different colors, right? So by definition, n colors suffice. So if you have a rich palette of colors, graph coloring is easy. Okay? The problem is that we're usually interested in trying to figure out what the smallest number of colors is. And the smallest number of colors with which it is possible to color a graph is called its chromatic number. Okay? Any questions about that? Okay, so as an example to think about things, the chromatic number of a cycle, I claim, is a simple cycle of vertices, is either going to be 2 or 3, depending upon whether you have an even cycle or an odd cycle. Okay? Notice here we have an even number of vertices in it. We can color it orange, yellow, orange, yellow, orange, yellow, and it works out fine. Okay, the place where it now meets something, it meets a vertex of the other color. When we have an odd number of vertices in the cycle, okay, then I claim that 3 colors are necessary and sufficient. Okay, certainly it's sufficient because you can start coloring them alternating red, blue, red, blue, red, blue up until the last vertex. There's no problem, certainly, because each one of these is different than its neighbors. The only problem is the joining point. If we color that one red, color that one a different color, okay, then we in fact have no contradictions. Okay, and it should be pretty clear that there's no way to color an odd cycle with less than 3 colors. Okay? Any questions about that? Okay? Now, what if I give you a complete graph? Okay? A graph on n vertices, okay, where every pair of vertices is connected to everybody else. How many colors do you need for a complete graph on n vertices? Okay? How many colors? N. Okay? You know that no matter, the only way you could hope to save something is if there were 2 vertices that you color the same way. But for any pair of vertices you pick that you say, aha, I want to color these 2 guys the same color. Well, if it's a complete graph, there's going to be an edge between there. And you're stuck. There's no way you can color that one. Okay? Any questions? How many colors does it take to color a tree? Let's stop and think about that. Suppose I give you a tree. How many colors does it take to color any tree? Okay. I claim 2 colors suffice to color a tree. Why is that? Can anybody think of a proof that 2 colors suffice to color a tree? Stop and think about that. Okay. Question, yeah? Say 1 color per level. Well, you can give 1 color per level. What do you mean by a level? Okay. Let's stop and think what you mean by a level. Does that mean that you pick up 1 vertex of the tree and you want to say that you sort of draw it something like this, right? Okay, and what you want to say is you color all of these guys, I think I got 2 colors here so I can be multimedia. We can make this guy red, this guy blue, blue, this guy red, 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 okay? So one thing that's true is that in a tree, because you can take 1 vertex, sort of pick it up by that, okay? Every vertex is going to be a unique distance from that vertex to the root. If it's an odd distance, okay, like here the distance is 1, we'll color it a different color than the root. If it's an even distance, okay, then we'll color it the same color as the root, okay? And this certainly would prove that 2 colors would suffice, okay? Can anybody give another proof that 2 colors suffice to color a tree? Okay. The proof that would come to my mind, I guess, is, well, let's try an inductive proof. Okay, suppose, let's say, that it's true up to, certainly on 1 vertex can be colored by 2, right? Let's say here's a tree on 2 vertices. Certainly we can color this one red, blue, everything's fine. Okay? In general, suppose I could color any tree of up to n-1 vertices, okay, using 2 colors. How could I now use this to color any tree of n vertices with 2 colors? Well, I know any tree is going to have at least 1 leaf. It's going to have at least 2 leaves. Why don't I take a tree on my tree of size n, delete 1 of the leaves temporarily, color the rest of it using 2 colors. The leaf that I had deleted is going to be connected to how many other vertices? 1. If this one was, if it was connected to a blue vertex, what can I color this guy? Red. Okay? And so that's sort of an inductive proof that you can get away with 2 colors for any tree. Okay? Does everybody sort of see that? Okay? So that's good. Okay? Now, in general, it's not so easy to find the chromatic number of a graph. Okay? So, for example, here, let's look at this graph up here. Zoom it in. I claim this graph can be colored with 3 colors. Okay? Why don't you, as an exercise, sit down now and do it, just to get some feeling for what's involved here. Okay, can anybody color this thing with 3 colors? Okay, I haven't done this for a while, so let me see if I can figure this thing out. Okay, let me just think if I was going to do it. Let's see. Okay. How many people have it? Okay. How many people don't have it? Okay. Let's think a little bit more just to see if we can figure it out. Okay. How many people have it now? Okay. We're starting to get a quorum. How would I do it? Well, I found that, in fact, again, it's probably maybe more than one way to do it. But the secret that I think I would use if I were trying to color it is if I knew I was going to be allowing to use 3 colors, I'd look at one of these triangles, at least the way that I did it. This was the way I did it. Okay? I colored my 3 colors 1, 2, and 3. Okay? The important thing to see was that I guess I colored this one 1, 2, and 3. I colored one of these triangles. Okay? And if I knew I was only allowed to use 3 colors, then in fact, once I fixed these 2 colors, this other one was fixed. And then once I fixed these 2, that one was fixed. Okay? And so now I fixed this thing, and this edge also fixed that color. Okay? And so now that everybody was fixed, I just had to pray that this was connected to 2 that were colored differently. Okay, and that's how I managed to color this with 3 colors. Okay, so 3 will suffice. Why can we show that 2 are not sufficient? Can anyone give a quick proof that 2 is not sufficient? Yeah? One of the edges being of degree 3 is not by itself a problem. Let's take a look at an example of something that has a very, very large degree. It in fact can be colored with 2. Snowflakes. You all know snowflakes are white, okay, but actually they're white in one other color, okay. There's one color in the center, which you don't see because that's little, that's pink, okay. But the bulk of the snowflake is white, okay. So here we have a graph with high degree where only 2 colors suffice. So the degree by itself does not force a high coloring number, okay, okay. It's sort of the connected thing. So the fact that here we've got a triangle, 3 mutually connected things, those provide constraints that make us forced to color this thing with 3. Right? A good way to think about it is, suppose I just gave you 1 triangle. There you know you need at least 3 colors, right? Now suppose, let's say, I require 3 colors to do this. If I add any extra edges or vertices, the amount of colors I need can't go down. Okay? If I'm stuck forced for 3 in a small part of the graph, then adding vertices and edges can only make it harder. Okay? So 3 is, we've just proven, is necessary and sufficient for this graph. Any questions? Okay? Good. Now, a very special class of graphs are the graphs that require 2 colors. Well, let's think of it this way. How many graphs require 0? What graphs require exactly 0 colors? Do 0 colors suffice to color? Well, the ones without any vertices. Okay, so 0 colorable graphs are very uninteresting. What graphs are there that it's sufficient to color with 1 color? What graphs can you color with 1 color and not have any contradiction? Any number of points that don't have any edges between them, right? This would be a perfectly fine 1 colorable graph. A snowfall, not a snowflake, okay, would be a 1 colorable graph. Okay? So the smallest interesting number of colors, I claim, is 2. The moment you add one edge, suddenly you're doomed to having 2 colors, right? So the interesting case, the smallest interesting case, is the graphs that where you have, which require 2 colors. And these we give a name, which you may have heard. I think we've used this word before as we've been talking about lectures. We say a graph is bipartite if it can be 2-colored. Okay? So here we have a classic example. The classic drawing of a bipartite graph is one where you put vertices on the left and vertices on the right, and all edges go between left vertices and right vertices. That, I claim, is a 2-colorable graph. Why? Which are the vertices? What's the coloring? We're going to color the left vertices one color and the right vertices another color. Okay? Because there is no edge that hangs around between 2 left or 2 right vertices. By definition, okay, once you have a partition of those vertices appropriately, that is the coloring. Okay? And bipartite graphs just come up a lot in a lot of applications. You know, for example, if let's say these were going to be, you wanted to try to map people, potential workers, to potentially acceptable jobs. That's naturally, let's say you're trying to match workers to jobs. It's fairly natural to have a set of people vertices as workers and a set of task vertices as jobs. You're never going to have one job do another job, so there's never going to be any edge between pairs of jobs. And in this problem, there's never going to be an edge between pairs of people, okay? Because we're trying to map people to jobs. So a lot of graphs are naturally bipartite, okay? And that's interesting because they give us properties that we can exploit in algorithms and in lots of things, okay? So for example, we showed a few minutes ago, any tree could be colored by 2 colors, right? Really, the reason for that is that a tree is simply a special case of bipartite graphs, okay? So there's lots of graphs that are bipartite, okay, that are not trees. So for example, a checkerboard graph is a good example. Okay? This, I claim, is a bipartite 2-colorable graph. How would you do it? Well, the way you do it in a normal checkerboard, right? Because checkerboards are 2-colored. You would make all of these guys white. Actually. And the other guys will leave as black. Okay, and I guess we'll continue on down there. Okay? So, bipartite graphs are important, okay, because those are the exact, defined as the ones that can be 2-colored. The other interesting characteristic of bipartite graphs is that every edge in a bipartite, every cycle in a bipartite graph is of even length, okay? Does that make sense? Let's stop and think about it. It should make sense. Why? Because every cycle is going to go from the left to the right, to the left to the right, to the left to the right. If you're going to get back to where you're starting from, you have to have gone left the same number of times you've gone right, correct? So that argues that certainly it's true that every cycle in a bipartite graph has to be of even length. The other interesting thing that's not quite as obvious is that, in fact, this is an if and only if condition. If the graph only has even length cycles, then in fact it is bipartite. Okay? So it should be clear that given any 2-coloring of the graph, you can prove that if once I can 2-color it, that means that all the cycles have to be even length. The interesting thing is it works the other way around. That once you're given a graph of only even length cycles, okay, that in fact that graph is 2-colorable. Okay? Does anybody see any ideas how you might prove such a thing? Okay, it's a trickier thing, and maybe I'll get into trouble trying to do this on the fly. So one way you might try to prove such a thing is you'll say, well, okay, so we now know that if the graph is bipartite, every cycle is even length. Let's now say that every cycle in the graph is even length. Does the graph have to be bipartite? Well, that means now can we show you that there's a two-coloring if there is an even length cycle? Well, it should certainly be clear that if I have an even length cycle, 1, 2, 3, 4, 5, 6, I could color that with two colors arbitrarily, right? If I have another cycle, let's put it here, that's separate from that, I could color that with two colors arbitrarily. Okay? If these two graphs share a vertex, the interesting thing, let's say now I have another cycle of even length. I stick on there. Okay? I could color this thing in one of two ways. Either I could color this thing either 1, 2, 3, 1, 2, 1, 2, or 2, 1, 2, 1. Okay? With a vertex in common, that would force the colorings to be the same. Okay? That now, in fact, I could show that given this cycle, okay, I could now, if there's only one vertex in common, then then that forces which one of the two colorings I give to the other cycle. Okay? Suppose now I have two cycles. Okay, let's say here we've got, again, 6 of them. Let's say I now have two cycles that have two vertices in common, okay, or more. Let's say that we have this cycle 1, 2, 3, 4. Okay? I claim that either in this case, I can number can I do the numbers consistently? 1, 2, 1, 2, 1, 2. Here, in fact, that defines the numbering on the other ones. Suppose that when I added the cycle in between, actually 1, 2, 1, 2, what is this? This is 1, 2, 3, 4, 5, 6. Suppose I add a cycle like this, let's say to there. Okay. Here I've numbered this one 1, 2, 1, 2, 1, 2, 1. Wait, 1, 2, 1, 2, 1, 2, 1, 2. Okay. Here I've got an edge from 1 to 2. Again, here there's no odd cycle. Okay. It's possible for me to interleave two even cycles so as to create an odd cycle. So, for example, suppose I had done the following. Sorry about this. 1, 2, 3, 4, 5, 6. Suppose I put one in like this that went from there to there to there to there. This was number 1, 2, 1, 2, 1, 2. Here I've got a problem. But the reason why I've got that problem is because, in fact, there was an odd length cycle. So that's not meant to be a proof. Okay, it's a little bit, you have to be a little bit careful here to show it. Okay, but it is sort of to convince you of the plausibility that it works both ways. Okay, any questions about that? Okay, so it's a useful thing to know. This is a property that turns out to be useful because, again, bipartite graphs occur so many times. Okay, now in general, the problem of finding the minimum number of colors you need to color a graph is an NP-complete problem, meaning there is no fast algorithm known for it or destined to be known for it. So testing whether a graph is bipartite is easy. You just start from one vertex, color it red, all of its neighbors get colored blue, and you just sort of walk back and forth. So two coloring is easy. Testing whether a graph can be colored with 3 colors is already NP-complete. Okay? So, you know, in general, you can't get an algorithm to find the best schedule for things. Okay? But there are various heuristics that can be used or various bounds that can be proven. Okay? For example, there is some kind of a connection between the chromatic number of a graph and the degree of the vertices. Okay? There's speculation here about this a little earlier. In fact, you can show that for any graph, the chromatic number of that graph is less than or equal to 1 plus the maximum degree of that graph. Okay? So in fact, if you have a graph that always has low degree vertices, in fact, you never need to use too many colors for it. Okay? So I guess if we think about the exam period problem, if we keep all the classes very, very small, okay, then we've got very, very few to any one class. There's going to be very, very few conflicts with it, right? Because if you have very few students and we have each of them take very few classes, you need very few exam periods, is really what that's sort of saying. Okay? So this theorem says, for any graph G, the chromatic number is less than or equal to 1 plus the maximum degree. How can we prove it? Let's look at a proof by induction. Okay? Here we're going to do our induction on the chromatic number itself rather than on the number of vertices. Okay? If the chromatic number of the graph is 1, what's the maximum number degree of any vertex? If we have a graph of chromatic number 1, it has no edges, so the maximum degree is 0. And lo and behold, we do get the case 1 plus the maximum degree. So you see that you can, in fact, get something that's larger than the maximum degree. We already saw that in the case of odd cycles, actually. The odd cycles were vertices of degree 2, but chromatic number 3. Now, let's assume that for all graphs of chromatic number less than n, okay, that the chromatic number of the graph is less than or equal to 1 plus the maximum degree. Okay, we've proven it for chromatic 1. Okay, we can assume it's true to some point. Now let's think about a counterexample. Okay, okay. Let's think about well, not counterexample. Let's think now about the smallest, okay, n chromatic graph, meaning something that requires n colors, but the leading any vertex, excuse me, leaves an n minus 1, a graph you can color with 1 less color. Okay. Now here we have some graph G, which by our assumption was n minus 1 chromatic. Okay, because here we have a vertex we're going to delete in any one of them. This vertex here had this graph here had the property that now, because we deleted it, it was colorable with n minus 1 colors. Okay, and because it was not a counterexample itself, okay, the maximum degree here was okay the maximum degree was at least. Let me think. Was that at least or at most? Okay. The maximum degree is at least this big. Okay. We now have this vertex here. If we now want to take a look at this vertex and see if it's colorable with n colors, notice that if this vertex was adjacent to less than n minus 1 vertices, we have the property that that we can color this vertex in such a way that the number of colors does not increase. Correct? If you have a vertex graph here that was colored by n minus 1 colors, okay, and we have a vertex here that isn't yet colored, but is adjacent to less than n minus 1 vertices, then by definition, we can color it. We have n minus 1 different kinds of paint. We've used at most n minus 2 different kinds of paint. Okay, adjacent to it, that frees up 1 color paint, which won't cause any kind of a contradiction. Okay? If it's not true, okay, that this is on adjacent to n minus 1 vertices, Then what we have here is a vertex of degree n minus 1, which is what we need, we said had to exist if the graph was n chromatic. Okay? Any questions about that? That may seem a little hand waving. Okay? But again, question. Okay. There are lots of interesting problems that turn out to be related to coloring. Okay. Some related to coloring paint, some, as you see, related to scheduling. Okay. Anyway, the general idea of a degree bound on graphs can be precisely determined by something called Brooks' theorem. Okay. Brooks' theorem states that any graph is n colorable if its maximum degree is n. Okay. Unless it is an odd cycle, which is what we saw before. The odd cycle is an example of a graph where it's got degree 2, max degree 2, requires 3 colors. Or it contains a kn plus 1 as an induced subgraph. What do we mean by an induced subgraph? Well, that means that if we delete all the other vertices, okay, the only edges that are left are, you know, the ones that are adjacent by the vertices we didn't delete. It should be clear that if you have a complete graph on n minus plus 1 vertices, every vertex is only degree n, and yet it requires n plus 1 colors. Okay? So it should be clear that both of these are contradictions to the idea that the chromatic number is bounded by the degree. Okay? And in fact, Brooks' theorem states those are the only exceptions. Okay? Any questions? Although, as we've seen before, you can actually have a graph which has high degree and yet a small chromatic number. Okay, there's no reason why that can't happen. But it means if you have low degree, you can't have high chromatic number. Any questions? Okay. Now, the place where graph coloring became most famous, okay, is with the 4-color problem. How many people here have heard of the 4-color problem before you came in this class? Yeah, a bunch of people. Okay, the 4-color problem was one of the, maybe in the pre-Fermat's theorem proof days. Okay, possibly the most interesting, famous open problem in mathematics. Okay, and that basically said that the 4-color problem, in the way that you were probably stated it in class, asked the question: I give you a map. Okay. A map consists of countries are of the form of regions. All countries are connected. We don't have a situation. What's a disconnected country these days? Used to be Pakistan was a good candidate, but then Bangladesh became independent. Any disconnected countries? Michigan is a disconnected state. Okay, and let's leave it at that. Okay, so we live in a world where we're given a map, okay, of countries, where every country is in one piece. Okay, we want to print the map. We want to color different countries, neighboring countries, different colors so as to highlight their borders. Okay, and the question then goes: how many colors do you need? If you're a person who prints maps for a living, how many colors do you need to guarantee that every single map you can print? Okay. They redraw a lot of maps these days in response to wars and things like that. But no matter how the borders settle, how many colors do I need to own to know that I can color every single map, okay, on any possible planet, okay, so that no two neighboring countries have the same color, okay? The conjecture was, for over 100 years, that in fact 4 colors sufficed. Okay, and here we have an example of a graph where 4 colors sufficed. There's the orange, A, and G. B, F, and D were yellow. You've got the blue, and the green. Here we have an example of a planar graph where 4 colors suffice to paint it. Okay. Now my claim is that the 4-color problem basically states that every planar map can be four-colored. Now, it takes a little bit of work to go from the problem of coloring maps to coloring graphs, okay? Because if you remember, what we were coloring in graphs was we were coloring vertices. Here we're coloring regions. The difference is that we can show, though, that you can reduce the problem of coloring regions to coloring vertices of a planar graph as follows. Let's represent each color, each country, by a vertex. Okay, maybe the capital city of the country. Okay? Now, we're going to draw an edge between capital cities, okay, of neighboring countries. Okay? So, here we have, in this case, we would draw an edge from here to that capital, that capital, that capital, and actually this is only 3 neighbors. Okay? My claim is if we do that, we have a graph where the vertices represent countries, and an edge between any pair of vertices representing countries that have to be colored differently. Okay? So it should be clear, and if not, please ask. I claim that by doing this, I have reduced the problem of coloring maps to coloring graphs in the way that we're used to talking about coloring graphs. The only thing that, any questions about that? You have to be convinced about is that in fact the graph that we get here is a planar graph. Okay, while I was gone, you guys heard a lecture about planar graphs. How do we know that this is a planar graph that we get, this so-called dual graph that we construct? Why do we know it has to be planar? Well, your countries were planar to begin with, right? Now, for it to be planar, we have to show that none of the edges cross, that there exists a way to draw that graph. So none of the edges cross, right? That's what it meant to be planar. Well, in the country, none of the edges crossed, okay? And now we can sort of, since we represent each vertex by a point, we're simply going to have to make sure that from our point, central point, to all of its neighbors, we don't have any of the edges cross within our country, right? But it makes sense that should be possible. If I have a, a country here, I can draw an arbitrary number of lines from my capital city to go out to the boundary without crossing each other. Does everybody agree with that? I could certainly even, let's say that I have a lot of countries here. Maybe we have a country that sort of sits out on the ocean. There's nothing wrong with me having lots of different edges going through a narrow region and not crossing. Okay? So it's certainly true that I could have any number of edges roam from my point to any point on my boundary without crossing, just so long as I keep the order of the vertices correct. So what am I going to do? How will I go and color these things? From my first one, I'm going to take one country, draw my edges from my country till I hit the boundary of each other country. Keep filling this thing in, and certainly I can always draw when I'm unconstrained, I can always hit the edge of my, hit the boundary with as many points as I wish. Okay? Likewise, once you specify on my boundary what points I want to reach, okay, it's a trivial matter for me to order my lines so that none of them cross. Okay? And so I can meet in that middle, okay, at each region and guarantee that none of those edges cross. Okay? I don't know, that may have been a little hand-wavy, but this is actually something you should see and believe. And if you don't see and believe, ask me again. Okay? How many people see why this graph has to have the property that you can draw it in the plane without crossing? Okay? Anybody skeptical of this? Okay? Can you use Euler's formula? Euler's formula is a property of planar graphs. So one thing that's true of planar graphs is once I convince you that this is a planar graph, Euler's formula tells you a lot of things about it. One thing it tells you is that there's not that many edges in this graph, is there? Okay. What did Euler's formula tell you? Told you the number of edges was less than or equal to 3n minus 6, right? Does that sound familiar? So this tells me that the number of borders I have to worry about is relatively small. It's not the case that I can have n countries connected to each of n other countries, which is good because with the world the way it is, the more neighbors you have, the more friction you have. Okay? This says there can't be too many neighbors in a planar graph is really what it says. Okay? So Euler's formula tells us properties of this thing once we know it's planar. The fact that it's planar is because we have just shown how to draw it in the plane. Okay? That's why we know that it's planar. Any questions about that?
Yeah. Isn't it v minus e plus r equal to 2?
Okay. There's a couple of different ways to write Euler's formula or implication of Euler's formula. Euler's formula said that, did I always get that right? What did it say? V
minus e
plus r equals 2. This is the truly Euler's formula, if you want to be thinking about it. Okay? This is, in fact, a corollary of Euler's formula. Okay, that's actually more useful for what I'm needing. Okay? But in this particular case, what does it say? In this case, for our planar map, V is the number of vertices in the plane. Okay? In this case, the number of vertices here in this graph is going to correspond to the number of regions in that graph, right? So one interesting thing to say is that in here, the number of vertices and the number of regions in one graph is the same as the number of regions in the other. Okay? And it's sort of a duality relationship between the faces here and the vertices here, which is why, in fact, we call the planar graph we get by changing the role of faces and vertices. We call that a dual graph. Okay? Just for sort of a useful operation to take. Okay? What Euler's formula shows is that there's some kind of symmetry between that. Okay? The dual graph here is a way of creating a vertex for every region. Okay? And I think you can say a region for every vertex. Okay? Well, anyway, it's that I don't want to dwell on that. But the important thing here is that it should be clear that given any planar map, you can construct a dual of that. And that has to be planar. Okay? And this captures the information we need to color it. Okay? Any questions? Okay? This should be, I want this to be clear. So if this is not clear, I do want some questions. Okay. So when we ask about the four-color problem in graphs, what we really want to know is true or false. Can every planar graph be four-colored? Okay? Can anybody show me a planar graph that cannot be colored with three colors? Let's think about it. Let's say that Skinner's conjecture is that every planar graph is colored by three colors. Can anyone show me a planar graph that is not colorable by three colors?
K4.
K4. Oh, so Skinner's conjecture didn't last very long, did it? Okay. Here is an example of a graph on a planar graph. It's perfectly planar. Nothing's crossing. Okay. I can color this guy 1. That means I'm forced to color this guy 2, 3, and 4. Okay? And so 3 colors certainly won't suffice. In this case, 4 colors will. The key issue to the 4-color question is it always true that every planar graph could be colored by 4 colors? I've proven 3 are not enough. The 4-color conjecture says, are 4 enough? Okay? Any questions? Well, again, it turned out to be an interesting and tricky problem. Okay? I mean, in some sense, you may think it's obvious. Okay? Because one thing you know about planar graphs is Kuratowski's theorem. Kuratowski's theorem said it doesn't contain a K5. Right? Okay, that's really what Kuratowski's theorem says. If a graph had a K5 in it, then that would mean that it was a, That would mean that it was a that meant it required 4 colors. But just because it doesn't actually physically contain a K5, there might be other ways in which you could have the graph that would require 5 colors. Okay, just because it doesn't have this particular graph in it doesn't mean that's what it takes to make 5 colors. Okay, so it turned out to be a tricky problem to try to prove. Okay, the history of it is interesting. Okay, it was originally stated in 1852. It was first proven in 1879, with a proof that lasted 11 years till it was broken, meaning someone proved that their proof was wrong. Somebody else proved it a year later. That proof lasted almost as long, okay, before someone found a hole in that proof. Okay. In fact, in 1976, it was first proven that every planar graph could be 4-colored, using a very, very famous proof that involved a tremendous amount of computer computation. How many people have heard this story in some context before? Okay, it's interesting. The 4-color problem was when I was a young man growing up, I heard of the 4-color problem. You heard about it in school. It was cute. You know, it was easy to explain. I remember once drawing pictures and coming up with a graph that required 5 colors. Okay, but of course it didn't require 5 colors. Okay, it was just that I couldn't figure out a faster way to do it. Anyway, back in 1976, it was proven that in fact every planar graph uses 4 colors, can be colored with 4 colors. Okay. And the way they did this was doing a lot of serious mathematics to getting the point down to where the problem was a finite-sized problem, where they could say, look, every planar graph, I've just proven that every planar graph is 4-colorable if these 1,800 things are true. And they then wrote a computer program to test each and every one of these 1,800 things. Something that took 1,200 hours of computer time in those days. Okay? And at 1,200 hours later, it said 4 colors suffice, and they were famous. Okay, a lot of people found this not very convincing. Okay, computer programs may have bugs, may have a lot of other things, but since then, people have written programs that do this thing much faster. Now the computations can be done in a day, as computers have gotten faster, and people have looked into these proofs more. So everybody now believes 4 colors suffice. Okay, and it's an interesting example of a different kind of a strange kind of proof based on computation. Okay? Any questions about that?
You said 4 colors suffice. 4 colors is the minimum amount of colors that we can have.
When I say 4 colors suffice, that means any planar graph on however many vertices you want, okay, 4 colors will be enough to color it. Okay? It doesn't necessarily mean you need 4 colors. We could imagine the case of, let's say we live in a country, a world where every country is its own island. 1 color would suffice. Okay? But I'm telling you is that any graph on n vertices, no matter how big n is, if it's a planar graph, 4 colors will be enough. Okay? Any questions about that? Okay, it's kind of an interesting thing and an amazing thing to be true. Okay? Now, proving that 4 colors are sufficient is obviously a complicated business, okay? I'm not going to give you this proof, okay? But I will show you what I think is really one of the most beautiful proofs in graph theory I've ever seen, which is in fact that 5 colors suffice, okay? That in fact I'm going to now convince you that every single planar graph you could color with 5 colors, okay? In fact, these other guys say 4 are enough, but I will prove to you rigorously that 5 are enough. Okay? Any questions? Okay? Well, first of all, the way I'm going to do it, okay, is by giving you an algorithm. I'm going to give you an algorithm that takes any planar graph and uses at most 5 colors to finish the job up. Okay? How do I do that? Okay? Well, first of all, I'll claim if I have 5 vertices in that graph, okay, then I claim I can 5 color it, right? You just color them all different vertices, that you believe. Okay? I'm now going to assume by induction that any planar graph okay, on up to n minus 1 vertices can be 5 colored. Okay? So now, you know, for n equals 5, you can do it. Now let's assume that for up to n minus 1 vertices, I know any planar graph on 5 vertices, on n minus 1 vertices can be 5 colored. Now, let me show you now how to color any planar graph on n vertices with 5 colors. What I'm going to do is find its lowest degree vertex. Okay? What do we know about planar graphs? You know a lot about planar graphs from the last lecture. Okay? What is the lowest degree vertex of a planar graph? It might be degree 0. It might be degree 1, 2, 3, 4. I claim any planar graph has a degree of a vertex of degree 5 or less. Why is that? Why does every planar graph have a vertex of degree 5 or less? Does anyone know why? Okay, by Euler's theorem. Okay? What was the consequence of Euler's theorem that I thought was most interesting? The number of integers is less than or equal to 3n minus 6. Okay? What is the sum of the degrees of any graph? Okay? The sum of the degrees of any graph, okay, is going to be equal to twice the edges. Do we agree with that? Therefore, the sum of the degrees of the graph is less than or equal to 6n minus 6, right? Now, if we have n vertices, what is the average degree? The average degree of a vertex in a planar graph is at most n minus 6, okay, over n, no, 6n minus 6 over n. That means that the average degree is less than or equal to that, which means it's less than or equal to 6 minus 6 over n. What does that mean? The average degree of a vertex in a planar graph is less than 6. Okay, only a little bit less than 6, but less than 6. If the average degree is less than 6, somebody's got to be less than 6. Correct? And if you're less than 6, we live in a world where degrees are integers. Ka-chunk, somebody's got to be less than or equal to 5. Okay? So do you see that argument? Okay? It's an important point. It's something like if we take a look at, if everybody's salary in here is $2,000 a month, okay, there is somebody here who is making at most $2,000 a month. Okay? And that's really the same argument we know here. So, based on Euler's theorem, we know that every planar graph has to have a vertex of degree at most 5. Right? So, let's say I delete that vertex. What do I know about what's left? Okay? I claim that by my inductive assumption, okay, the rest of the graph can be 5 colored. Does everybody agree that's what my inductive assumption is? Can anybody use just this observation to prove that every planar graph can be 6 colored? Let's look a little simpler. Just the fact that we have every planar graph has a vertex of degree 5. Can you prove to me that every planar graph can be 6 colored? Okay. That I claim is easy. Why? Suppose I now go and I just take a look at I know that I've got my planar graph here. Here I've got my vertex of degree less than or equal to 5. Suppose I delete a vertex from a planar graph. Is it still going to be planar? Let's think about that. Of course it is, right? Okay, it's not going to suddenly create any lines that are crossing. If I have it drawn in the plane, I just cut out a part of the paper. No problem. Okay? So suppose, let's say I delete this vertex of degree less than or equal to 5. I now want to prove that if I want to prove that this graph is now 6 colorable, how can I do it? Well, 6 color the rest of it. This vertex here is connected to at most five other vertices, right? If I'm allowed to use 6 colors, I claim I always have a free color to finish the job, right? So if, in fact, I want to say that 6 colors suffice, 6 colors are easy. Start out with the planar graph, find a vertex of degree 5, delete it, find another one of degree 5, delete it, delete it, delete it, delete it, delete it. Eventually I get down to one vertex, color this thing pink, blue, and I'll go back and add the vertices. Okay, every single time I do, okay, I always have at least one free color. I will color it that way and keep going. So does everybody here believe that 6 colors are enough? Any questions about that? So 6 colors are easy. Okay?
So you're saying that once you delete the vertex with the degree 5,
yes,
then you continue deleting them, and then when you start adding your vertex, you're going to color.
Right. So let's take a look at a concrete example here. Let's have one more. Sorry about that. So here I've got a planar graph, right? I'm going to find a vertex of degree to show that 6 colors suffice. Well, I find a vertex of degree less than or equal to 5. Let's say this one here. I delete it and color the graph as I wish. I'm allowed 6 colors. Maybe I'll color this one 1, 2, 3. Maybe I'll color that one 2. Maybe I'll color that one 4. I now put this vertex back. This guy's adjacent to at most 5 different colors, right? If I'm allowed to use 6 colors, I can pick the color that isn't used. And there's got to be one that isn't used, right? So I can color this one what? I could color it 4. No, I could color it 5 or 6. Let's say I want to color it 5, just for the sake. Okay? So 6 colors I claim is easy. But you can see 5, I'm going to be living with less constraint. Now what's the problem? If, let's say, I want to 5-color the graph. Suppose, let's say, that I delete this vertex, color the rest of it with 5 colors. It might be the case that I've got something like this, where all my 5 vertices are of different color neighbors. Now I want to color myself differently, but I don't have any color. I don't have any slack, right? Looks like I'm in trouble. Okay, but I'm not in trouble. Okay, let's look at why that is. Okay, so I pick the lowest degree vertex of my graph. If the vertex was of degree less than 5, and I want to 5-color the graph, then it's easy. 5-color the graph, I've got at most 4 neighbors. That frees up a color. I can color myself in such a way that I cause no trouble. Right? Everybody agrees with that. So the trouble is going to come as follows. Suppose that the vertex I just picked to delete had the property that it was a vertex of degree 5. Okay? So now what's the situation? I have now deleted this vertex V. I have 5-colored the remaining graph. Suppose I came back and my 5 neighbors, let's say this was colored red, 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 blue, green. Let's say that I only used 4 colors among my 5 neighbors. Is there a way I can color myself to make everything happy? Sure. So long as these guys, I have not used all 5 colors among my neighbors, there will be 1 free color for me to color myself and 5-color the graph. So the only trouble I'm going to get into is now I have taken my vertex, it's a degree 5, and in my 5 coloring of the underlying graph, all my neighbors are different colors. Looks like I'm stuck. Okay? But what am I now going to do? I'm now going to recolor part of the other graph. How do I do that? Well, let's say what I'm going to do now is induce a subgraph. Let's say I take a look at this situation here. I'm going to take a look at this. We know this is colored 1, this is colored 2, 3, 4, 5. Let's say I now take a look at all the vertices in the graph that are colored 1 or colored 3. Okay? And just think about those vertices and the edges between them. Right? There might be a lot of vertices in the graph that were colored. There's n minus 1 vertices in the graph, except plus this one here, which isn't colored yet. Let's look at the ones that are colored 1 to 3. Are there any two vertices of color 1 that are next to each other? No, can't be. Is there any vertex of degree 1 that's connected to one of degree 3? Could be. Okay, could be the situation I got something like this. So here is V. I could have a vertex here of degree of color 1. It might have a lot of neighbors who are colored 3, right? Each of these vertices that are colored 3, do they have any neighbors that are colored 3? No. Do they have neighbors that are colored 1? Possibly. Okay. Let's just think about all the graph induced by the degree, by the vertices colored 3 and 1. Okay. The graph, if we delete all the other vertices, we're going to get a bunch of different connected components in the graph, right? Well, let's think about it. Suppose we get a situation where this vertex here, the vertex of 3, color 3 directly neighbored to our guy, suppose that it is not in the same connected component associated with vertex 1. So this is a separate component here. Is there anything we can do? I claim in any connected component here, I could reverse the roles of two different colors. Okay? Let's think about it. Suppose I have a graph that's 5 colorable. Okay, and it's colored purple, green, yellow, orange, and red. Suppose I want to just reverse the roles of yellow and red. Is that going to create any contradictions? No. So let's say I repaint this thing. All of these in this component that are 1, color them 3. And all the ones that are 3, color them 1. What is going to happen? Is it going to create any contradictions? Not if I do it in the whole component. It isn't, right? But what might happen if I do such a thing? Okay, what might be my potential win by recoloring this component? Okay, what could I hope to gain? Now, instead of this being colored 1, now this vertex is going to be colored 3, right? So if this guy, if I've gotten rid of this guy, now I could color this guy 1, right? If I get rid of the color 1 from here, then that would free up color 1 to go here. Is there any problem that might happen, though? Let's think about that. Suppose I take this connected component and recolor, reverse the roles of 1 and 3. Am I definitely going to free up a spot for color 1? Is there any reason I might not free up a spot for color 1? Well, what if this connected component here included this vertex? If I reverse the role of 3 and 1 in this entire component, what has happened? Yes, this is now colored 3, but what's going to happen here? It's colored 1 now, right? I haven't really solved any problem. Okay? Does everybody see that? That in here we've got a connected component. Repainting all of the 3s and all the 3s 1s, okay, hasn't really solved any problem if these guys are in the same connected component. Okay? All I've done is rearrange things. Okay? How many people are still with me? Okay, any questions? Okay? How can I solve this problem? Well, we agree if V1 and V3, let's zip down. do not belong to the same component, then we can reverse one of the colors, free up one of the colors. The only trouble we get into is if, in fact, there is a cycle, okay, or that these are in the same connected component, right? But let's think about it. Suppose there is a 1-3 coloring from here to here. Is it possible that there is a 2-4 cycle from here to here? Okay? Let's now consider the induced graph of the vertices colored 2 and 4. Those also might form a connected component, right? If the connected component of the 2 and 4 colored vertices from here doesn't reach there, then we could recolor this thing to make this thing 2, and then free up that as color 4, right? Okay, it's the same situation as before. If, in fact, we had a component here, 2, 4, 2, 4, 2, 4, that didn't reach this, we could reverse this thing to make this colored 2. So we could free up that vertex to be colored 4. Okay? The only trouble we would get into is what? If there was a cycle of 1, 3, 1, 3, 1, 3 here, and a cycle of 2, 4, 2, 4, 2, 4, 2, 4 here. Okay? Then if we reverse the 2 4s, we don't improve ourselves. If we reverse the 1 3s, we don't improve ourselves. Okay? But can that happen? No. Why not? Because this was a planar graph. Okay? What does a planar graph mean? It means no edges cross, right? Here you see an edge cross, or maybe you would see it if my slide was dark enough. See that? We've got an edge crossing. There is no way that you can have these two cycles of different colors cross, because the lines don't cross. It might be that they meet in a vertex. But if they meet in a vertex, then that color had to be either 1 or 2, 1 or 3, and not 2 or 4. So this, I claim, is where we know why we know how we can do it. Okay? I'm going to give you this graph. You've colored the whole thing. Okay? Oh, sorry. I have given you this graph. Okay? You take that vertex of degree 5, recolor the whole graph except for it. I know the following things are true. Either one of the 5 colors is not used, in which case I can now color that vertex, or all 5 colors are used, but there is not a 1, 3, 1, 3, 1, 3, 1, 3 path, in which case I can reverse one of those. Does everybody see that? What I mean by reversing it? Okay. Or there is a 1, 3, 1, 3 path, but then we know that there cannot be a 2, 4, 2, 4, 2, 4 path. And so one way or another, we can either reverse vertex 1 or vertex 2. That frees up our color, okay, and therefore 5 colors suffice. Any questions about that? Okay. This, I think, is a very, very beautiful proof. Okay. And I just like to put this up here as a quick thing here. This is how I always feel when I see this proof. Okay. You go through this long chain of reasoning. Okay. And you get very excited. Go for it. Okay. It's interesting because here you see it's a fairly long step of reasoning. But it keeps pinning it down so we eventually know where we can get our extra color from. Okay? And so 4 colors suffice, but is extremely hard to prove. 5 colors, a reasonable proof suffices. Okay? Any questions about that? Okay? Any questions about graph coloring in general? Okay? Thanks. What I'd like to do, and I know I'm leaving this a little bit short of time, but I ran a little longer than I'd like. I'd like to do the course evaluations now. so let me pass out the forms, and here's these. I'm thinking about these. Okay, sorry about this. Okay, pencils I'll give out in a second. Hold on. So start propagating these. Sorry. Let's try these and these. And let me start passing pencils around. Okay, so here, start passing these around. Sorry about this. Here you go. Sorry about that. Sorry about that. Go ahead. And any pencils that you have here, somebody have pencil here. I'll take forms. Okay, there you go. You can pass these around and put any extra pencils you have in. So what should you put in here? I'm sorry about this. So what is the interesting information? The department is, the course number is CSE 547. Yuck. If you want to write it in a different, so I would write CSE 547. The section, I don't know what it is. Maybe let's say 01 for importance. The instructor number, my instructor number is 25936. Okay, so that's 25936, and probably we should let other people write that. See the original one. And my name is Skina, in case you haven't figured that out. S-K-I-E-N-A. Again, the important thing for me is to know comments. Okay, comments like "the prof sucks" is not a useful comment. A comment that "the prof sucks because," okay, is one. You can sort of, if you explain why. Okay, and so I'm interested very much in your comments. I haven't taught this course for a long time, and the world may have changed in some ways, or there may be things that you're interested in letting me know. Please let me know. Okay, I'd like to know. Okay. And I guess for those people back at Ademco, I guess you guys don't get these things. How have you handled this in the past?
Can you hear us?
Hello? You don't. I'm not hearing you.
Can you hear us? Hello?
Okay.
I think we're just getting it back.
Sorry about that.
We're getting it echoed
Okay.
back, but he's not hearing.
I guess. Yeah.
Hello?
Hello? Yeah.
Okay.
They mailed us the forms and we mailed them back.
Okay, so I mail you the forms and you mail them back. Okay, I will
Sure.
do so, and when I send you your homeworks, I'll send you the forms with them, and we'll deal with that.
Okay.
Thanks a lot. I'll see you guys. Okay. Yes. Take care. See you guys. Okay, thanks.